Today we're going to talk about inverse trigonometric functions. So we'll start by talking about what an inverse function is. So a function, it looks like it's f being raised to the -1 power, but that -1 actually represents inverse. So that's read f inverse of x is called the inverse function of f of x if and only if when you compose the two functions together, f composed with f inverse, you get x. But also when you compose it the other way, f inverse composed with f will also give you x. An inverse function is essentially what undoes a function. So a function, remember, is like a machine. You stick an input in, it does a bunch of stuff and spits out an output. Your inverse function is going to take that output, undo all the stuff the machine did, and give you back your original input. So it turns out that the domain of f will be the range of f inverse, and the range of f will be the domain of f inverse. So in other words, if the ordered pair a comma b is on f, then the ordered pair b comma a would be on f inverse. So their domain and their range, or their x's and y's, are switched. So this means that f inverse is a reflection of f of x over the line y equals x, as shown below. So here we have a function f, and notice this has the ordered pair 0, 3 and 1, 4. When we switch that, 0, 3 becomes 3, 0, and 1, 4 becomes 4, 1. And so it switches your x and y values. So it's a reflection over that line y equals x. So again, if you drew this in wet paint, folded the paper over the y equals x line here, it would press down, it would paste this inverse function here. Now if you wanted to verify that two functions were in fact inverses of one another, so if you had two functions f and g, and you wanted to know if they truly were inverses of one another, then you would verify that f composed with g of x would give you x, and that g composed with f of x would also give you x. So, a definition for you. A function, remember a function, every x has one y, but we talked about how a function where different x values could give you the same output y. Well, a function is called one-to-one if every y has only one x. So, like with a function where we can use the vertical line test to tell if it's a function, we can use the horizontal line test to show that it is a one-to-one function. So a one-to-one function, not only does every x have one and only one y, but every y has one and only one x. So if we wanted to determine if it was a function, a one-to-one function, we would first have to determine if it's a function, so this does pass the vertical line test. And then we would determine if it's a one-to-one function to see does it pass the horizontal line test, and it does. What about this one? This is definitely a function. It passes the vertical line test, but as you can see, just even looking at the x-axis, it touches 1, 2, 3 times. So the line y equals 0, that horizontal line touches more than once, therefore it's not going to be a one-to-one function. What about the parabola here that we see? Does it pass the vertical line test? Yes, so it's a function, but is it a one-to-one function? No. What about this one? Now, it does pass the horizontal line test, as you can see, but it's not a function because it fails the vertical line test. So if it's not a function, it certainly can't be a one-to-one function. Now, fact, a one-to-one function has an inverse, and only one-to-one functions have an inverse. If your function is not one-to-one, then it cannot have an inverse. It does not have an inverse. What we can do sometimes, though, is we can restrict our function, our domain of our function, so that it is a one-to-one function, and therefore it will have an inverse. So let's just look at this right here. Look at this parabola right here. If we were to switch the x's and y's, so we have the ordered pair 0, 0, which would be 0, 0. We have the ordered pair 1, 1, which would be the ordered pair 1, 1. The ordered pair -1, 1 would be the ordered pair 1, -1. And see how it would fail the vertical line test here? So that's why your function has to be one-to-one, because if it fails the horizontal line test, when you switch your x and y's and your x's now become the y values, if you have more than one y value, when you switch them, you're going to have more than one x value, and it's going to fail the vertical line test. So therefore, it can't be an inverse function. So let's look at x squared, the parabola x squared, which we just talked about. So as we can see, this is not going to pass the horizontal line test, so it's not a one-to-one function. So it's not going to have an inverse. Because again, if we switch, these multiple y values will become multiple x values and it'll fail the vertical line test. However, notice the range of this function here is all positive values and 0. So it's 0 all the way up to infinity. It's just from 0 to infinity, all the positive values, anything bigger than 0, is repeated on this side. So we have double values. Now what if we got rid of those double values? What if we restricted this function x squared for just x greater than or equal to 0? And when we do that, then it's just this half of a parabola right here. And this half of the parabola here, which repeats these values here, so all the outputs are accounted for, but now they're only represented once. So now not only does it pass the vertical line test, it also passes the horizontal line test. So this is a one-to-one function now. And if you think about it, what undoes x squared? It would be the square root of x. So it does have an inverse, but it only has an inverse for the positive values. Because if you think about it, when you take the square root of x, we have to restrict that domain that x has to be greater than or equal to 0. So now let's talk about how we can find the inverse function. So what did we say? We said the inverse function is the inverse of f of x, where the domain and the range are just switched. So that's exactly what we'll do. We'll just switch our x's and y's, if you will. However, we call it f of x, so let's go back to calling it y. If we just switch our x and y and solve for y, well, that gives us our inverse. But of course, we want to do that last thing where we check because we're studying and we want to make sure it works. So we'll compose f and f inverse, and then we'll compose f inverse and f and make sure it really does give us x. So let's look at an example. Let's find the inverse of f of x equals the cube root of 3x plus 2. So first step, we'll call that f of xy. Then we'll switch our x and y, and we'll solve for y. So we'll have to get rid of that cube root, so we'll cube both sides. Now we need to get rid of that 2, so we'll subtract 2 from both sides. And now we need to get rid of that 3, so we'll divide both sides by 3. And so x cubed minus 2 all over 3 is what we solved for y. So if we did this right, that should be our inverse. F inverse of x should be x cubed minus 2 all over 3. But let's check. And to check, here is my f and my f inverse. I'm going to compose them together and make sure that I'm just left with that original input x. So we'll do f composed with f inverse first. So into f, I'm going to put the entire f inverse function. So look at what f does. It's the cube root of 3 times your input plus 2. So the cube root of 3 times whatever the input is, which happens to be f inverse, plus 2. Now notice this 3 and this 3 are going to cancel. And so once they're gone, we have the cube root of x cubed minus 2 plus 2. The minus 2 and plus 2 are going to cancel, and I'm left with the cube root of x cubed, which is x. So it did work that way, but we need to check the other way. So taking that same f and f inverse functions, now we're going to do f inverse composed with f. So into f inverse, we're going to plug in the entire f function. So what does f inverse do? It does your input cubed minus 2 all over 3. So whatever's in the parentheses, which happens to be f, cubed, minus 2 over 3. Now this cube root and cube are going to cancel. This plus 2 and minus 2 are going to cancel. And now the 3's are going to cancel, and we are left with x. So we are able to show that that is truly the inverse function to this function f here. So now let's apply it to our trig functions. Let's look at our trig functions sine, cosine, and tangent. Are they one-to-one? Would they have an inverse? And how can we adapt the domain if they're not? So let's first look at the sine. There's the graph of the sine. We've talked about that before. Notice it's this oscillating function that goes up and down and up and down and up and down, and it's bouncing between -1 and 1. Well, as you can see, that's definitely going to fail the horizontal line test. So what if we were to restrict the domain? What if we restricted this graph? But we have to keep the range the same. Now, the range of the sine is all values between -1 and 1. So what if we just went from one set where we went from -1 up to 1 and we deleted everything else? Now, looking just here on this restricted graph from -pi/2 to pi/2 does have an inverse, right? This is a one-to-one function. All the outputs from -1 to 1 are accounted for on here. And this is a nice one-to-one function that would have an inverse. Let's look at the cosine. Here's the graph of the cosine, and again, it's that nice oscillating function bouncing between -1 and 1. As is, it's not going to have an inverse. So what if we restricted the graph and we just kept all values from 1 down to -1 and we deleted everything else? Now it is a one-to-one function and it would have an inverse because all the outputs are accounted for. Everything from -1 up to 1 is accounted for on this restricted graph here. And now let's look at the tangent. As you can see for the tangent, those repeating kind of S-shaped curves here, it's not one-to-one. It fails the horizontal line test. But what if we restricted it and we just took this middle S-shaped curve right here and we got rid of all the rest? Now it is a one-to-one function and it will have an inverse. So we have to restrict the domain. So for the sine, we had to restrict the domain between -π/2 and π/2. For the cosine, we had to restrict the domain from 0 to pi. And for the tangent, we had to restrict the domain from -π/2 to π/2. So here's the definition of our inverse trig functions. For the sine, we either call it the arc sine or we call it looks like it says sine to the -1. It's not sine being raised to the -1 power. That's sine inverse or inverse sine. A lot of times we just call it the arc sine. And what it means is that if y is equal to the arc sine of x, that means that the sine of y is equal to x. And so remember, for your inverse function, the domain and the range are switched. The range of sine is -1 to 1, so that is now the domain of your sine function. These should be closed brackets. I apologize, that's a typo on my part. We should be including -1 and 1. And now remember, we restricted the domain of sine to make it one-to-one, so now we have a restricted range that the range of the inverse trig function is from -π/2 to π/2. For the cosine, the inverse function is the arc cosine or the inverse cosine. What that means is that if y is equal to the arc cosine of x, that means that the cosine of y is equal to x. Again, we're switching the domain and the range. The range of cosine is now the domain of the arc cosine. These again should be square brackets. I should be including -1 to 1. And then we restricted our cosine graph from just the angle 0 to pi to make it one-to-one. So the range of the arc cosine is just the angles between 0 and pi. And for the tangent, its inverse is the arc tangent or the inverse tangent. If y is equal to the arc tangent of x, that means that the tangent of y is equal to x. Switching the domain and the range of the tangent and the arc tangent there, that would mean that the domain is all real numbers. But remember, in order for the tangent to have an inverse, we had to restrict its domain. So we did right here. So the only outputs you can get for the arc tangent are angles between -π/2 and π/2. Now notice, when you're figuring out what the inverse function means, it means that the sine of y equals x, the cosine of y equals x, the tangent of y equals x. These y's, which are equal to the arc sine, arc cosine, and arc tangent, are angles. So when you're taking the arc sine, the arc tangent, or the arc cosine, you're getting out an angle. All right, so we're going to stop here. We're going to pause, let that sink in, and we'll reconvene for some examples in just a little bit.